All right. So local, linear, and differentiable. What's the difference between them? Really nothing, right? You could do the same thing for this one. Let's do this one quickly. G of x equals the absolute value of x minus 2 plus 1 at x equals 2. So using the calculator, and I just got rid of it, but let me reload it. Y'all know where to get the absolute value button? Yeah, math. You can always find something in the catalog. The catalog is the second function on the 0, and then it's listed in like numerical order and then alphabetical order. But here's how you could do it. You hit math, and then you click to the right to number, and it's right there, number 1. You talk about a good pep rally cheer, right? Math number what? 1. Math number what? 1. Math number 1. Louder, Brandon. Math number 1. 1. There it is, absolute value. And in math print, it gives you the absolute value. So here we go, x minus 2. Click to the right, plus 1. And zoom 6. We know what this graph's going to look like. The parent function is the V for victory graph, and the vertex is moved over from the origin to the point 2, 1. Now we want to zoom in at 2, so hit trace first, type in 2, and there you go. Is this function continuous at the point 2, 1? Is it continuous? Is it connected? Yeah, it is. Okay, now let's zoom in. Zoom number 2. And we should be pretty dang close to the origin. You do have to kind of recalibrate it. Just move your little cursor around. I zoomed in, and it's still got the V there. Okay, so now I hit enter, and now the X and Y axis disappeared. If you're not right at X equals 2, you're going to have to like recalibrate every time. Just kind of move it around. Is it flattening out? Can you tell? Is it starting to look linear? Golly, I've zoomed in quite a bit, right? And it's still looking like a V for victory graph, right? Now, if we're looking for, if a victory to us is turning into one straight line, then this V for victory is kind of mocking us, right? Kind of like Brandon is me. You know, it's just like, V for victory. It's not straightening out. See, I don't get mad, Brandon. I just get even. Hey, look, there you go. And I do apologize. Hey, look, I've zoomed in so many times. I'm not just standing on planet Earth anymore. I think I'm kind of at the molecular level. And it's not straightening out, right? So intuitively here, because I cannot zoom in and have it turn into its tangent line, G is not, I almost wrote differentiable, is not locally linear, okay, also known as, AKA, diffable. It's not differentiable at x equals 2. And you would expect that, right? You would expect that because your parent function is the absolute value of x. And what does the absolute value of x do? What's the slope coming in from the left on the absolute value of x? Anyone? It's -1, right? The number in front of your x in the absolute value is like mx plus b. That's your slope, plus or minus. So it's -1 coming in, and it's +1 going out. Well, it's the line on either side. So does -1 equal 1? No. So we wouldn't expect it to be differentiable. And then the -2 just moves it over 1, 2, and then the +1 moves it up 1, right? So this is 1, 2, this is 1. So right there, we know the slope is not the same. And we do have the visual cue. I heard, was it Ella, you said it? Yeah, that's what it is. M equals -1 from the left, M equals 1 from the right, and then visually there we have a sharp turn. Which really, in mathematics, yeah, we can call it a cusp, okay? Cusp. So that's now one of two visual cues that we have to determine if something is differentiable at a point or not. It's not the ultimate test. The reason that it's not differentiable is not because of the cusp. You don't say that this function f is not differentiable at the point 2,1 because it's got a cusp there. The cusp is a consequence of how and why it's not differentiable. If you were really to justify, you could say f of x is continuous but not differentiable at the point 2,1, since the slope from the left of 2 is -1 and the slope from the right of 2 is +1, and -1 don't equal 1, right? Or doesn't, right? Equal 1. All right. What's the other visual clue? Do your math homework. We're testing Thursday. Anytime you have a sharp turn or a cusp, and then where else is it not differentiable? Yeah, not just a jump, but at any discontinuity. Any discontinuity. All right. So let's jump to example 12. Example 12, we're just going to give ourselves a visual cue and an example of an equation where something is not differentiable. So let's look at this function on 12a. F of x is 2x plus 6 in the absolute values, and we're sketching it at -3. Now, if you want to sketch this graph, just like we did, the parent function is the absolute value of x. That's your slope, your 45-degree slope coming in, bounces at the origin, 45-degree slope going out. If you want to put it in a standard transformation, look what you can do. You can factor the 2 out on the inside. And if you do it on the inside, that's going to be a horizontal compression by a factor of 2. If you take my arms at 45 degrees and you push them horizontally toward each other, it's going to make my arms steeper. Right? Now, you can also pull a constant multiple out from inside the absolute value as long as you make it positive. So this is the same as this. It's mathematically the same. But notice by transformation, it's a slightly different way to get there. Instead of pushing my arms horizontally by a factor of 2, you're vertically stretching me by a factor. You're grabbing the tips of my fingers and you're pulling up by a factor of 2. But it accomplishes the same thing, okay? It makes your slope now twice what it was. So instead of -1 to 1, now it's what? -2 and 2. That's your slope coming in and going out. And what does the +3 do to any graph, including this, when it's on the inside? Shifts it to the left 3. So here it is. This is it, right? Let's go ahead and sketch the graph then. Give yourself an x-axis and a y-axis. I'm going to copy this. Copy this. Copy. Copy, Roger. Okay. So the vertex is at 1, 2, 3, -3. And then it comes in like this. We'll just come in, boom, and boom. And I'll go ahead and write this. M is -2. M is 2. You can always get the slope of these absolute value functions simply by looking at that coefficient of x. Whether it's on the inside or outside, doesn't matter. And then it's going to be plus or minus. So it's just because it's +2 on the inside or -2, whatever. One of them is going to be plus, one of them is going to be minus. And it's not always negative to positive. If this thing had opened down, if there had been a negative out front, now it would be increasing and decreasing. So there you go. We could say that right here, f is not differentiable or locally linear. I'm not going to write that. We're going to say at x equals -3. Okay. Is it because the graph has a sharp turn or a cusp there? No, it's because -2 does not equal 2. I'm not going to write that. But here is your visual cue, right? You have a sharp turn or a cusp. They're really the same thing. People typically classify this one as a sharp turn rather than a cusp because it goes from a straight line to a straight line. But, you know, it's not, the cusp is the formal math term for any type of barb or something that you'll see on there. All right. Now let's look at this one. F of x equals the cube root of x. After today, this should be a parent function. This is the inverse function of what? If you cube root a number and you don't mean to, how can you get it back? Cube it, right? So the cube root of x and x cubed are inverses of each other. Remember, and this is just a quick little review, how do we find the inverse of a function graphically? Opposite reciprocal? Flip it, right? To get the graph of an inverse, you have to flip it across what line? This line. Y equals X. If you take a graph and you reflect it across the line Y equals X, you get the graph of its inverse. So it'll look something like this. Okay, if you turn your head at a 45, you'll see that they're mirror images of each other. Okay, so that's just a review. Reflect it across the line Y equals X, and now you get the inverse function. Now, let's go ahead and draw that so it's not obscured by X cubed. Here's what the cube root of X looks like. It comes in. Now, let me use a contrasting color. I need to borrow some of y'all's palettes. Y'all have some really good colors. It still has origin symmetry, okay? It has rotational symmetry. But what do you notice about 0? Is the function continuous at 0? Is it connected? Yes. Oh, yeah, it's connected. Big time. Now, back in the high school days when I was a skater, if this were out there somewhere, I'd be finding it. I'd be skating on it. And I'd be probably falling down without pads and getting another concussion. Right? Yeah. And with all the concussions I've had, you know, hey, what career choice do you want? Can I teach math to high school seniors with all my concussions? No, we wouldn't recommend that. Okay. And here I am. Whatever. Why would I be looking at that for skateboarding? Because it's connected. That's cool. But what type of tangent line do we have right there? What are skateboarders looking for when they're skating? They're looking for what we called, we're looking for vert, man. We're looking for vert. We want to go vertical. And guess what type of tangent line we have there? Yeah, we have a vertical tangent line. So X cubed, of course, has a horizontal tangent line at the origin, which is why its inverse has a vertical tangent line there. And what's the slope there? Yeah, it equals, in this case, it equals infinity or dne. I'm going to put f prime of 0 equals dne. You could do that over here as well. We probably should have done that. F prime of -3. I wrote the sentence, but f prime of -3 equals dne. It doesn't equal infinity. It equals dne. Over here, it equals infinity, which remember is another type of dne. So this is the one that you have to be careful about. Vertical tangents are smoothly connected, aren't they? But they're vertically smoothly connected. Vertical is off limits, right? We can't go vertical here because the slope is undefined. So this one you have to be really careful about, right? Be on the lookout for this. It's smoothly connected, but it's a vertical tangent line, right? Now, if you're ever given an equation like a x cube root of x, you're going to have to know it's vertical. If you're ever given a graph and it's made up of like a semicircle or something, then you'll be told that the graph has a vertical tangent at whatever, the endpoints of the semicircle. And that's going to trigger in you, non-differentiable there. Now, x to the 2/3. This guy is just a modified version of x to the 1/3. Another name for it is the cube root of x squared. Okay? But this should be a parent function after today. All you have to do to get that function is take these orange y values and square them, right? What's that going to do to the positive y values? It's going to increase them, right? Like 2 becomes a 4, 3 becomes 9, so it's going to make it steeper. What about the negative y values down here? -3 becomes positive 9, right? -4 becomes positive 16. So this one is going to look a lot like, if you remember back like in little school, your teacher gave you like a piece of paper and you were like, okay, today we're drawing seascapes. And you're like, okay. And so you drew like an ocean all right? And you could draw with me. You drew an ocean, and then you colored it blue, right? And then maybe you said, ooh, I know what I'm going to put in my ocean. I'm going to put a shark, right? And there's my shark. He's in the ocean. And then of course you had this guy in the corner, always in the corner, right? You had the sun, and then the rays could be like long, short, or they could be squiggly, short, squiggly, whatever. And then of course, I remember this. I did this too. The sun, always wore sunglasses, remember? Because man, it's bright on the sun. You always wore sunglasses. But no seascape was complete. No seascape was complete without the final touch, right? The birds. There's your seascape. I guess the sun was smiling too. Okay? And then maybe you drew like a little fish in here. Okay? So this is what this graph looks like. Okay? If you take the other graph and you reflect it, it becomes steeper. And now it has y-axis symmetry. Okay? So what is the derivative at 0, do you think? The same what? I mean, I said this one was infinity or DNE. Is this one still infinity?
Negative.
Kind of. And then it's what? Well, look at the slope from the left side. From the left side, the slope is approaching positive infinity. It goes vertical right there. But it's coming in decreasing, right? So it's negative infinity. What is the slope approaching from the right-hand side? That's a positive slope, everybody. So positive infinity. Oh, so now it's negative infinity from the left, positive infinity from the right. Take your pick on why this derivative doesn't exist. Negative infinity doesn't equal in positive infinity. No negative number equals a positive number or negative idea. Or it actually goes to infinity, which is vertically steep. So this is DNE. All right? This is, again, what we call a cusp. Now, this is a special cusp that actually goes vertical. You can have cusps like my seagulls over here. These don't necessarily go vertical, do they? So you can have a cusp that comes in like at a 45 and then goes out at a 45. That's still, it doesn't matter. But this one is special because they both go vertical at the origin. So this is your bird graph, x to the 2/3, okay? Now, look at this graph itself. You didn't realize back in the day, but your graph is full of non-differentiable points, isn't it? Right? The tip of every one of these wave crests is a sharp point, continuous but not differentiable. Look at the tip of the shark, right? That's continuous but not differentiable. The seagulls themselves. Look at the fish. He's got tails that are not differentiable. Oh, man. And the sun? Well, the sun is cool, right? Each of his rays are past the vertical line test, and they are differentiable. But a lot of calculus in this little picture, right? A lot of calculus. All right, and then the last example that we're going to give is something we've already talked about. What's the parent function for this guy? Square root of x, right? The parent function is the square root of x. And remember, that graph is the upper half of the parabola that is not tipped over. It's reflected across the line y equals x, and we take just the top part of it. But remember, it started off as a parabola. We only look at the top part. Now, real quickly, we already talked about this. Is this function continuous at 0, its left endpoint, the genesis point? Is this fun? Yes, it is, right? We talked about how a function be continuous at an endpoint of a closed interval. We can loosen up the 3-step definition. What would be the slope of the tangent line to the graph of x squared at the vertex? What type of tangent line does it have? X squared at the vertex. What's the tangent line right there? 0, right? It's a horizontal tangent line. Y equals x squared has a horizontal tangent line. And so when you reflect it across the line y equals x, it becomes what? Vertical, yeah. So we do have a vertical tangent line right there on the graph of the square root of x. And we've mentioned this already before we really even knew what differentiable was, you know, rigidly. The function was continuous at 0, but was it differentiable at 0? No, it's not, right? And you can analyze the domain of any function to determine where it's differentiable. And we did that up here. I think we did. Did the intern do it? No, we did it right here, right? When we found the derivative function, which was this right here, we noticed that x could no longer equal 2. 2 is in the domain of the original function, right? 2 minus 2 is 0, the square root of 0 is 0, but it wasn't in the domain of the derivative. So the derivative knows that it's not supposed to be differentiable at the genesis point. So anyway, what does this function look like? Well, let's put it into standard transformation form. First thing I'm going to do is flip the two terms around. And then on the inside, if you ever have a negative input, you have to factor that negative out, and it gives you x minus 10. Now let's review transformations. What does a negative in front of x multiplied do to any function, including this one? Which axis? Y-axis reflection. Good. It's real easy if you think about what it's doing. It's a negative in front of your x values. So take two x values, like this, side by side, and say they're now the opposite of each other, right? Negative 5 becomes positive 5. Positive 5 becomes negative 5. They switch across the y-axis. And then, of course, then the minus 10 would be right 10. Okay, so let's see what that's going to look like. I don't call it the vertex. I call it the genesis point, just because it's where it starts. But here's 10, and now it opens to the left, so it still comes up vertically, and it looks like this. So what would f prime of 10 be? F prime of 10? 0? No, that's f of 10. F of 10 is 0. The y value is 0. But what's the slope right there? Kind of. Yeah, you could say negative infinity, maybe. But here's the problem with negative infinity. Remember, the derivative only exists if it's the same slope from both sides, right? From both sides. Can we even calculate the slope on the right-hand side of that genesis point? No. So, I don't know. It's DNE for sure, okay? We're not going to define differentiability at an endpoint like we did for continuity because it doesn't exist. If it's an endpoint, it's not going to be differentiable there because we need two sides. So again, DNE is kind of a catch-all category for a lot of different things. Things can fail to exist because, in this case, the slopes aren't the same from both sides. The derivative can fail to exist because it goes vertical, or it can fail to exist because there aren't two sides. And yes, it does in fact go vertical here. So from the left side, it is approaching negative infinity. And from the right side, it's like, ¿Dónde está? Okay, so DNE. So there you go. There's kind of like, these are places on a graph where a function is continuous, but not differentiable, okay? Continuous, but not diffable. It's worth just re-emphasizing that. There's an example. You should kind of have one of those examples, or at least a transformation of one of those examples, equation and graph, like in your derivative pockets, in case anyone ever asks one. All right, now here's a very important theorem. It says so right above it. Very important theorem. It's not like the squeeze theorem of the IVT. It's just a theorem. If f is differentiable, then it's continuous at a point. We write this in logical terms as D implies C. That's what that means. Okay, and then this arrow here is just points to. Okay. Too many arrows, right? Yeah. D implies C. Remember in geometry you had statements, if-then statements? If D, then C. That's the statement. I'll put the statement in front. STMT. Okay? So that's kind of cool. If you know a function is differentiable, you know it's got to be continuous, right? It's got to be. Now, you remember the other types of statements we had? You had the inverse, you had the converse, and then you had the contrapositive. Okay? Contrapositive. In an if-then statement, here's how you get the inverse. The inverse is you just negate them. Okay? So not D implies not C. This little symbol here means not. In logic, it's like a fallen over L. Is that a true statement? If it's not differentiable, then it's not continuous? Not in an if-then statement, that's not necessarily true. Do we have an example why it's not true? All of these up here are examples, counter examples, we would say. These are not differentiable, yet they are continuous. So in any given statement, the inverse is not necessarily true. The converse flips them around. C implies D. Is that true? Just because a function is continuous, does it mean it's differentiable? No. Do we have a counter example to disprove that? How about any of these, right? They're continuous but not differentiable. Okay, so this one's also not true. But you know which one is true? The contrapositive. The contrapositive is a combination of the inverse and the converse. It negates the opposite. And this one is true. And we know this one already. We'll finish with this for today. If a function is not continuous at a point, then it's not differentiable. We've already talked about that, right? Any discontinuity then, a jump, a hole, a vertical asymptote, it's not going to be differentiable. All right? So there you go. We'll finish right there. There's only one page left. We'll finish it tomorrow. That means the worksheet will be due on Wednesday. And we're testing on Thursday. Have a super awesome, splendid rest of your day. You're off to a really good start.